Hello, period 6, and welcome to another edition of Algebra Class Online. This is the very last page of the homework from Lesson 2, and again, that's Lesson 2 in Unit 8. And I'll just highlight that down at the bottom, Lesson 2, Unit 8, just so you have a reference. So I hope you've been following along so far with this lesson. The last homework page I thought was pretty simple. And we finally have made it to a real-life problem where we can apply what we know in terms of how a quadratic function acts. Now, these are probably the most typical quadratic problems that you'll find. It'll be an object that's thrown up in the air, and it reaches a maximum height, and then it falls because of gravity, and it falls and reaches the ground. Now, question 6 says, the height of an object that is traveling through the air can be well modeled by the quadratic function that opens downward, meaning it will have a maximum. An object is fired upward, and its height in feet above the ground is given by the equation or the function h of t is equal to negative 16t squared plus 64t plus 80. Now, each one of those numbers means something. I'll try to depict what each one is telling us as I start to graph my function. Now it's saying that t represents time in seconds that the object's been in the air. Now, before we graph it, I just want to look at the graph that they supplied us. The y-axis is labeled with height above the ground. That's our rising and falling action. And the x-axis is labeled with time. All right, that's how long the object is in the air for. Now, I chose to graph this on Desmos.com. I told you guys about this site last week. I think it's a super easy graphing calculator tool to use. I highly recommend it. I almost like it better than the actual graphing calculator that we use in class, just because you can really manipulate the graph any way you want it, meaning like the window of the graph, and get the curve of the function to fit the window more perfectly. So I've already graphed that. I'll go to my screen on Chrome. And if you look at it, it looks as though there's a couple of specific points that we can find. The first one being the y-intercept. It looks as though it crosses at y equals 80. All right, now you'll see there's an 80 inside in my equation. I'll show you how that relates to that y-intercept in just a second. Let's look at the second point, which I think is pretty obvious. It's our maximum point of the graph. And it looks like it occurs along the line x equals 2. All right, that is the maximum height. Now, I don't quite know what the number is. It's obviously between 140 and 150, but again, I'll solve for that in a minute. And the last point I see is where it falls and crosses the x-axis, which it looks like it crosses exactly at x equals 5. Now, the x-axis is going to be our ground, or like our actual Earth in this problem. And you'll see that the x-axis always represents usually a height of 0 or the ground level of something. So now let's go back into our notes. And we're going to try to attempt to graph this. Now, we said that the y-intercept was 80. Now, how do I know the y-intercept is 80? Well, when the y-intercept occurs, the value of x is 0. Now, if I was to substitute x of 0 into my function and solve, I see that my t squared term cancels out, my t term cancels out, and I'm left with just 80. So h of 0, or my y-intercept, should equal that y value of 80. All right, so there's where that 80 comes into play. Now, we clearly said that it crossed the x-axis at 5. All right, now, that's a little bit more in-depth of how to find that 0. For now, we're strictly going to rely on the calculator to find that 0 for us, and it was pretty obvious. And 9 times out of 10, when we're dealing with a quadratic function, it will be an actual integer value where it crosses our x-axis. But the most important point that we probably needed to find on this graph was my maximum. Now, I'm drawing in a dotted line along the line, or the vertical line, x is equal to 2. We said that that was our axis of symmetry, and that the maximum occurred about there. Now, we said it was between 140 and 150. So, you're probably wondering, That's part B. How do I find that maximum height? Well, being that it occurred along the line x equals 2, I know I can now substitute a value in of 2 for all my x's, and in this case, t's, because we're looking at the x-axis being labeled as time. So the height of the object after 2 seconds of flight is equal to, and now I'll write my function and substitute in the value of 2 for every t that I see. Now solving that is super easy. You could use your calculator to solve it. You could do it by hand. I'll go ahead and solve it by hand. My 80 stays. 64 times 2 is 128. And it looks like I'll have a negative value. And it'll be 2 squared is 4. And negative 16 times 4 is negative 64. Now granted, negative 64 plus 128 equals positive 64 plus 80 equals 144. So we've now found the y value at my maximum point to be 144, which occurs roughly right there. And I will place a point along my vertical line of x equals 2. And it looks to be that I have all 3 points I need to connect my curve. Now, we said that the x-axis represents the ground level. We now know that the actual object is launched from something that is 80 feet above the ground and thrown directly up. Now gravity's taking over, and it reaches my maximum height, and then begins its falling action. And you'll see that it should fall. That was actually not that great of a curve, but it should fall 5 seconds after it was thrown up into the air, and it will reach the ground level. And our curve will look something like that. Now, you're probably wondering, why don't I ever graph in the negative direction when graphing falling objects? Well, if I graphed in the negative direction, I'd be graphing a time-traveled object. There's no negative time that we're talking about here. We're only talking about present and future. So that's why we always begin at our y-axis, and then there's always a rising action and then a falling action, ultimately where the object hits the ground. All right, so question C says, at what time does it hit the ground? Well, we've decided that it hits the ground 5 seconds after it was thrown. It rises for the first 2 seconds and then falls for 3 seconds. And question D says, over what time interval is its height increasing? Well, it's only increasing from 0 seconds to 2 seconds, and we can demonstrate that with an inequality where we start at 0, which is less than or equal to the time where it starts to rise, t, which is less than or equal, actually no, strictly less than 2, where at 2 seconds it begins to fall. So that inequality is just translated in English, means it's rising from when you throw that object up into the air until it reaches that 2-second point, and at 2 seconds it begins to fall. And that's it. Now, this is the first of many quadratic function problems that we'll do that involve real-world objects, or they like to do cannonballs sometimes, or a rocket was shot. And you'll see that they're all generally the same. They all have maximums. They all have a function that represents the rate at which they're rising and falling. And you'll be asked to identify the maximum. You'll be asked to identify the x-intercept, or the 0, or where it hits the ground. All three are the same thing. And usually you'll be asked to identify some type of domain in which it's increasing or decreasing. All right, hope you guys were able to follow along with this. Please post any questions you might have on Google Classroom. And please try to stay up with your notes. I know that we're slowly moving through this unit. We're on lesson 2. I'm planning on starting lesson 3 later in the week. All right, have a good day, guys.